first I want to thank the organizers, and especially Satoshi, for inviting me to come talk to you about something that I find really exciting. It started off as a side project, and it's now just flourished into this whole new project that it's taking all my time, but it doesn't matter because I like where it's going. So I'm going to get right into it. The topic, of course, of the meeting is what is creativity. I want to definitely tell you I'm not going to try to answer the question of what is creativity. You guys are much more adverse at that sort of question, but what I kind of want to do during this presentation is tell you at least one way of approaching this type of question. And one way is maybe asking questions like, what is interdisciplinarity? But, and I would like to say that those sorts of things might be related, I can't say for sure, but it's more about the approach that you might be able to take with this. So I will be a little brave, and I will say one thing about creativity, and I think one source of creativity comes from the flow of ideas. So one of the underlying forces behind the research, this area of research that I'm doing, is that science is about the flow of ideas. Ideas build on ideas, innovations build on other innovations. We collaborate over time and cross disciplines, and so this flow of ideas is something that kind of guides what I'm going to show you today. And I want to emphasize that it's not necessarily the products of science that I'm talking about today. It's going to be more the communication of scientific ideas. It's how we give credit to ideas and how they proliferate, where they come from, and where they're going. So I'll give you a little background into the philosophy of how I kind of approach this, my collaborators and I approach this problem. And it's the first way we tried was to take the physicist approach. And I don't mean to make fun of physicists because there's two physicists in our lab. And so, but they're really good, and not just because they're smart and they have good quantitative skills, but they choose the right problems. This is the sort of problem they choose. They choose a problem where the components of the systems they work with are interchangeable. They look at systems where there's regular structure. Unfortunately, the system that I'm talking about, since science is the flow of ideas, it's not quite that simple. The parts, it's much more, well, I mean, I'll go to that, but the idea is that the system is not interchangeable, it's not well mixed. We have, there are more things to deal with. And the social nature of science and the communication of science makes that. Engineers have a little different approach. They work on complex systems, but the complex systems they work on, I would kind of claim, and we've talked a lot about this in our lab, that they tend to have these sort of characteristics. They're pairwise, they're sequential, and they're purposeful. So their approach is different than, again, the approach I'm going to talk about. So I'm a biologist by training, and we work with systems that are much more differentiated. They're multipartite, not better for worse. They're multipartite, they're integrated, and they're incredibly dynamic. There's feedbacks, positive and negative, that you get. Not that you don't get that in physical systems, but so the question is, how do you deal with these sorts of systems? And the buzzword for the last 10 years, of course, has been networks. Networks is the solution to all problems. Well, I'm going to show you real quick that I don't think it's the solution, but it's a good first pass at these sorts of systems. So networks are, again, the philosophy that drives what we do. We have this idea of flow of information, of energy, of stuff, we'll say. And the networks, because they represent flow, they work well with the problem of science representing flow. So this is an example of a network that we see, and unfortunately, this is what we've been getting in the literature. They're really, really complicated pictures. This is the protein-protein interaction network, and really, there's not a lot to see. It's a beautiful picture, but unfortunately, it doesn't tell you a whole bunch. It's something that I have actually sitting in my office in all sorts of different colors, and really all I think the picture tells you is that someone has done a lot of work. So what we want to do is something different. Or not different, but we want to try to pull out the important structures in those networks and highlight those, kind of like a cartographer. So because we read a lot about cartography in our lab too, this is an example of what I mean. So here's a picture of Boston. I was recently in Boston, and this shows all the details. And let's say I gave you a task of trying to get from, let's say, Boston to Harvard or something. You could use this sort of tool, but unfortunately, it's too much detail. It has every tree, every car, every street. You need something else. You want more of what you really want a map. This isn't really a map. This is more of a picture. Instead of a picture, you want a map. You want something like this. This is what you need. It highlights the important details. this is what you need. And so that's what we're trying to do with network data today. In biology, we're inundated with tons and tons of data all the time. So this has been a challenge for us for a long time. And in the field of biology is, how do we make these sorts of things in those big, big data sets? So that's the goal. We want to simplify and highlight. We want to highlight the community structure. We want to pull out the salient facts in the data and find and see if there are stores. So now let's get back to the flow of information in science. So this is what we work on. One of the things we work on is citation networks. You can look at all sorts of different levels. You can look at author level, article level, journal level. And the beautiful thing about these particular networks is that they're weighted and they're directed. So a weighted and a directed network actually there tends to be lots and lots of rich structure in these sorts of networks. And so from that, you should be able to, you shouldn't ignore the structure that's in a weighted directed network. So the citation networks that I'm going to show you too come from large data sets that are just recently available. They've been available for the last several decades, but we're at a time where this is a good time to work on this sort of thing. And also, the coolest thing about it is when you look at these enormous data sets, it kind of represents the collective nature of all of science over decades of work, centuries even. We're actually now just starting on a data set that goes all the way back to Newton's time. So it's a lot of fun to actually see where these ideas are coming from, especially when we incorporate the time component. So the first data set I'm going to show you, we work on all sorts of data sets, but this is an example of one. This comes from Thomson Scientific JCR citation reports. We have well over 7,000. This is an underestimate. Well over 7,000 journals and closer to 10 million citations that we're looking at. So you get something that looks like this, and this is just a small smattering of this. But this is the idea. So again, this is a picture. It's not very useful. And I'm not going to go into the details, but the idea is that we use the idea of throwing random walkers onto this network, and we look at the distribution after an infinite amount of time. So it's similar to the PageRank algorithm that Google used. But again, it incorporates information theory, network theory, things that are just actually being developed in the last 10 years in this area of network science. So this is what you get. This is the first picture I'm going to show you, and if I have time, I want to show you a lot of the cool tools that we have. This was the first thing that came out of our lab that Martin and Carl actually produced this particular map. This is our first map. We have tons and tons of different maps now. But what you're seeing, the nodes here, represent the size, the time that a random walker would spend all of science on this database. And it turns out they spend about 26% of their time in molecular biology. They spend maybe not quite as much time in mathematics, but this particular map represents the frontier of science. We only go 5 citation years behind. You can go all the way, you can go 100 years, but this particular one is the frontier of science. So a lot of people looked at it and they go, no, this was actually what it looked like in 2000 or the late 90s. We're like, exactly, this is what it's representing. But the cool thing about this picture is that you can look at the links and look where the flow of citations are going. You can look what's connected and what's not connected. One thing that was interesting, the first thing that we saw with science is that it's not necessarily the ring structure that a lot of people thought at first. That a lot of people had written about. At least our data shows that it's much more like a U. That there's this connection out of operations, research, and statistics that you have to kind of go through the backbone, which is general medicine, molecular biology, chemistry, and general physics. But there's all sorts of things that have kind of sprouted out of this, just the first map that was created. And we have, like, the little ring that you see here, it doesn't show up really well there, but the ring that you see represents how much of the citation flow is exported to other fields. So something like general medicine, about 30% of its flow of citation goes out of general medicine, and economics, they're very much an in-group. They don't cite much outside their field. You don't see much of a ring there. But there's all sorts of things. By the time I talk to you all about these cool stories that are popping out of this map. Just like a regular map, you can use it as a tool.
Very brief question.
Yeah.
All the lines point to 2 arrows, so it's a bidirectional thing?
You got it. Thanks for asking that question, Harold. Actually, yeah, the arrows represent direction. So what you'll find, actually, maybe that'll take me to, I'll show you something really neat, is actually that there are some fields that only citations go into one field, but not vice versa. So what we found as a general pattern, that we get a lot of citations from the applied sciences going into the basic sciences, but not vice versa. So in statistics, you can't really see it, but citations go towards the statistics, but not vice versa. And you have fields where it's just the opposite. I can give you a better picture of this later after. You can do things like zoom in. You can actually zoom into this map, and this is the social sciences. And what you see when you zoom in, just like in a regular map and you add more detail, you start to see certain things pop out. Like in sociology, you see the institutional behavioral sociology pull apart. You see in psychiatry and psychology, the applied sciences pop out as you look at more detail. You look at all sorts of, there's all sorts of cool things, but I'm getting behind. So, of course, I could talk about molecular biology and general medicine, some things that we have there. One cool way of actually navigating this is one of the tools that Moritz in our group has designed. You can do things like, you can't see it very well there. Let's go to that. Well, where's my cursor? So you can do things like jump into psychiatry. You can go one step away. You can go into education. You see that only most of the citations in the last 5 years of all of the entire JCR database go into psychiatry from education, but not vice versa. You can go into education. You can look at education. Go back into here. Let's go into medicine. You can look at medicine. You can look at the top journals in those fields, or those. There's details on those journals that you can look at. You can also increase or decrease the level of detail that you have in these particular maps. So there's all sorts of cool things. This was actually one of the funner tools that we've developed, and we've had a lot of fun with, where you can actually go one step, two step, all sorts of really neat things. So, go back. Okay. So the question is interdisciplinarity. This is just brand new in the last, I would say, and I only have a short amount of time, so I might be going too much detail. But this is brand new. We've been thinking about it for the last 4 weeks, using some of these tools, these maps, these new apps that we're creating to mine through this wealth of information, these citation networks. We're finding that there are fields and there are journals and there are papers and scientists and researchers that fit like this field right here, where they're a bridge of information. They go to a conference like this, an interdisciplinary conference like this, and you see later on, you can dive down and you can look at that particular researcher and where they cited. And a lot of times it cites clear out of their field, which is, a lot of people like to say that interdisciplinary is an area of creativity within science. I can't necessarily say it is or isn't, because we're so early on in the project. But we now have tools in place where we're starting to ask those sorts of questions. You also get, I'm coming to realize it's really an issue between what I'm using the terms integrator, or we'll say synthesis of ideas and dispensers of ideas. There are people that receive lots of citations, and there are also people that give out lots of citations, and those have different effects on where ideas come from and where they're going. But let me just show you one more tool. I'll show you this last tool here that kind of gives you an idea of all science. So this is essentially the map right here. It doesn't show well on the screen. But essentially each square represents, again, the time that a random walker on this map would spend. So for example, if you're up here, you guess, that's the journal Nature, as everyone would suspect. This is where we're starting to get at the idea of interdisciplinarity. The circles represent the amount of flow coming from other journals. Red represents citation flow out, and the blue represents citation flow in. If you see purple, it means you have both. So if you go over to a journal like Science, you can see that it spreads. Actually, it spreads its ideas and gets its ideas a little bit differently than Nature. A lot of people think that they're the same, they get the same sort of thing, but they're spreading out differently. You notice that these are actual fields themselves. So over in economics, so interestingly, if you look at economics, that's over in the corner over there. And I go to the top journal in economics. What do you notice? Again, you find that sort of, for whatever reason, economists don't really cite so much outside of their field. Not always. Again, this is coarse grain. Looks like they have a few citations going into science up there. But you can do all sorts of things. You notice like some of the clinical journals, like I think there's the clinical journals. The clinical journals are always interesting to look at. But you get the kind of the idea. If you go into, I know a lot of people here are interested in physics, so you can go into chemistry. There's chemistry here. Astrophysics has a strong, what we call import factor with citations. Anyway, I can talk about these sorts of things all night, and I will if you want to. But the main thing, here's the summary. The scholarly literature forms a vast, incredibly rich data set. It forms a network where we can use a lot of new tools that are being developed, not just in our lab, there's tools being developed all the time. And you can mine this well. The one way of doing it is mapping and identifying the important structures using some of these information theoretic approaches. And then the other thing is, then you start asking questions, and that's kind of where we're at right now. What are the epicenters of science? Has science developed an institution where creativity is facilitated? So that's kind of where we're at. And everything that I talked about is available. We're a science lab. We're not a commercial product. Everything's freely available. So you can go to our website and look at a lot of these tools. We have to put them all up, but we'll have them all up really soon. So if you're interested in looking at any of this stuff, or you have questions about it, you're free to go welcome to look at that. But one last thing before I'm done, I want to note the people I work with. One of the reasons this project has been so fun is because these guys are a ton of fun to work with. Carl Bergstrom, Dr. Carl Bergstrom, he is a theoretical evolutionary biologist. Ted Bergstrom, who's an economist at UCSB. Ben Altos is an undergrad that works with me. Moritz has helped us with the apps. And Mark Montalvo is a physicist that also works on a lab and has done a lot of the information theoretic stuff. So without that, I'll take a few questions.
Thank you.